Good day. I am going to present a visual tutorial on the QR algorithm. This tutorial will focus on the dynamics of the algorithm in the case of positive semi-definite matrices. The QR algorithm works by taking an input matrix, call it A, and then finding its QR decomposition A equals QR. It then replaces A with R times Q and repeats. It repeats this over and over until the algorithm converges. In the case of positive semi-definite matrices, and more broadly symmetric matrices, the matrix A becomes diagonal whenever the algorithm converges. This type of algorithm is called a fixed-point iteration. A fixed-point iteration works by taking a function f and applying it over and over again to some starting value. When it converges to a fixed point of f. In general, the dynamics of this iteration is very complicated and is sometimes chaotic or even divergent. In the case of when f maps R1 to R1, we can visualize the dynamics using a cobweb plot. However, we cannot use cobweb plots to visualize the QR algorithm, as the function being iterated maps R4 to R4 instead of R1 to R1, at least when the algorithm is applied to a 2x2 matrix. We will instead use a correspondence between positive semi-definite matrices and ellipsoids. An ellipsoid is a hypersphere that has been stretched in perpendicular directions. Here we have an example of 3 ellipsoids. The one on top is a sphere, and the other 2 have been stretched in a set of perpendicular directions. The directions in which the stretching has taken place are called the semi-axes of the ellipsoid. A 3-dimensional ellipsoid has 3 semi-axes, and a 2-dimensional ellipsoid, called an ellipse, has 2 semi-axes. A positive semi-definite matrix is a symmetric matrix whose eigenvalues are all non-negative real numbers. Let M be a general positive semi-definite matrix. There is a 1-to-1 correspondence between positive semi-definite matrices and ellipsoids centered at the origin of a vector space. This correspondence is a very simple one. It is given by multiplying each point on the hypersphere by M. Conversely, from the ellipsoid, we can recover M. The fact that this is true is a consequence of the spectral theorem. This correspondence allows us to adopt a more geometric language when talking about positive semi-definite matrices and more broadly symmetric matrices as well, as long as we make some adjustments. We have an interactive visualization of the QR algorithm. The blue ellipse stands for a 2x2 positive semi-definite matrix. The red ellipse is the output of one iteration of the QR algorithm. We can see how the larger semi-axis of the red ellipse makes a smaller angle with the x-axis than the larger semi-axis of the blue ellipse. If we tilt the blue ellipse over to where the red ellipse was, we can see that the subsequent iteration reduces the angle further. We see that this is the case for every ellipse, and this is why the QR algorithm works. When the ellipse's semi-axes are parallel to the coordinate axis, the corresponding matrix is diagonal, and we may find the eigenvalues. We can also find the eigenvectors of our starting ellipse, but be aware that there is a caveat to this. We will discuss this caveat later. Notice that if the larger semi-axis is aligned to the y-axis instead of the x-axis, we also have a fixed point. This fixed point is unstable though, because if we tilt the ellipse slightly towards the right, then an iteration of the QR algorithm will tilt the ellipse further to the right. Likewise, if we tilt the ellipse slightly to the left, then an iteration of the QR algorithm will tilt it further to the left. Unstable fixed points are undesirable because the closer we are to them, then the more iterations it takes before the algorithm converges. Consequently, the algorithm takes an arbitrarily large number of iterations to converge. This problem can be fixed by changing the function to a discontinuous one. This discontinuous function ought to move the larger semi-axis closer to the x-axis if it is within a certain threshold of the y-axis. This helps to motivate Wilkinson shifts, but we digress. There is another problem with the algorithm, which is unsolvable. This problem manifests when the lengths of the semi-axes become very close to one another. When this happens, the rotation induced by one iteration of the algorithm is very small. We can only know the eigenvectors of a matrix once the corresponding ellipse has its semi-axes aligned with the coordinate axis. The small rotation makes it take longer for this happen. This behavior is a consequence of the violent instability of the eigenvectors of a matrix around repeated eigenvalues. A good example of this is around the 2x2 or 3x3 identity matrices. A small perturbation of these matrices can violently change the eigenvectors. Notice though that, while the eigenvector problem becomes unsolvable, the corresponding eigenvalue problem becomes easier. If a matrix is close to an identity matrix, its eigenvalues are approximately the same as those of an identity matrix. Moreover, the eigenvalues of a matrix vary continuously, while the eigenvectors conversely vary discontinuously. One might argue that this is not really a problem, because if an ellipse is nearly a circle, then one can change it into a perfect circle and trivially obtain the eigendecomposition of that instead. This does though violently change the eigenvectors of the matrix. Digressing, we remark that this visualization can be used as the basis of a proof of the convergence of the QR algorithm, at least in the 2x2 case. The lessons apply equally well to other iterative eigenvalue algorithms, like the LR algorithms. We can use the same technique to eliminate the unstable fixed points. This concludes our visual tutorial on the QR and closely related iterative eigenvalue algorithms. Good day.